Welcome everybody to the Physics Colloquium. I'm Roger Blanford, and it's my great pleasure to welcome Maura McLaughlin to give us the Physics Colloquium. Maura, I believe, was an undergraduate at Penn State University and then did her thesis work at Cornell in radio astronomy, and has become an expert in the use of pulsars in the service of physics and much else. And she's now a professor at the West Virginia University, and she's chair also of the North American nanohertz collaboration, and she's going to tell us about a 12.5-year collection of data, the results that have come from it already, and the promise of this going forwards. And the subtitle of her presentation will be "Knocking at the Gravitational Wave Door." So Maura, we're looking forward very much to hearing your talk. Share your screen and we'll listen to you.
Okay, great. Can everyone see that okay? Looks good. Okay. Yeah, so as Roger said, I'm going to be telling you about results from the NANOGrav Physics Frontier Center. And we are a collaboration who is using high precision pulsars to search for gravitational waves at much lower frequencies than LIGO. Let me tell you just a little bit about the collaboration before I move into talking about the science. So NANOGrav stands for North American, because we're a collaboration of scientists in the US and Canada. Nanohertz, because those are the frequencies we're sensitive to, so very, very small gravitational wave frequencies. Observatory for gravitational waves, because we are seeking to search for gravitational waves at nanohertz frequencies and characterize the low frequency gravitational wave universe. We're about 150 students and scientists at the moment. We've been an NSF Physics Frontier Center since March 2015, and we were just renewed. Last week, we found out that we'll be renewed for another 5 years. So that's very, very exciting. We have a website if you want to learn more about us. And I just want to mention here that we always welcome new members. We welcome participants at meetings. If you're interested in the talk today, feel free to get in touch and come to one of our meetings and learn more about what we do. We are also part of a much larger international collaboration called the International Pulsar Timing Array, or the IPTA. And so we combine our data with data from radio telescopes in Europe, in Australia, and now India. India just joined about a month ago to form like an Uber pulsar timing data set, which in time will be the most sensitive in the world for these gravitational wave experiments. It's not quite yet, but within a few years, the IPTA data set should be the most sensitive, more sensitive than the NANOGrav one I'm going to talk about today. Okay, so let me give you like the super big picture of the science goal we're trying to accomplish, and then I'll talk more specifically about our experiment. So this cartoon shows our picture of galaxy evolution over cosmic time. So the standard picture is that galaxies were born, and when they were first formed, they were very small and kind of irregular, and they've grown to be larger and more ordered through mergers. So we can test this picture electromagnetically through observations with normal telescopes, light, when galaxies are at separations like this, and we can actually resolve two galaxies that are in the process of merging. However, it's very hard to probe merging galaxies when they're at this stage, when they might look like just a single galaxy, and the black holes at the cores of these galaxies are at very, very small separations. So like less than a parsec with orbital periods of years. And there's lots that we don't understand about these final stages of the mergers of these black holes at the cores of these galaxies. And so with our experiment, instead of using light to resolve galaxies that are, very, very widely separated like this, we want to use gravitational waves to probe merging galaxies at these very, very close separations. And so this is our big picture science goal. This is what we want to probe, and the astrophysics we want to test. And just to talk a little bit about how we're going to do this, let's talk about gravitational waves. I don't think you really need an introduction to gravitational waves at Stanford, but just in case, this is the standard cartoon of gravitational waves. Here are two black holes in the process of merging. Gravitational waves are predicted by general relativity. They're ripples in space-time. They're produced by massive accelerating objects like binary systems, of course. They carry energy away from binary systems. So in time, these black holes are going to merge and produce a gravitational wave burst. like those detectable by LIGO. Just like LIGO, our NANOGrav experiment depends on measuring light travel time differences between objects. And so this is the standard little cartoon. If a gravitational wave traveled through the screen, these are how the proper distances, whoops, sorry, there we go, between the particles in this test particle ring would change. Gravitational waves have two polarizations, a plus and cross polarization. This really doesn't matter too much for our experiment, but the main point is that just like LIGO, our NANOGrav experiment is looking for changes in the light travel time between objects. Okay, you know all about LIGO here at Stanford. I'll just show this slide very briefly. I'm not going to talk at all about LIGO results. As you know, this has just been so exciting and just astounding. We've learned so much about stellar mass compact objects through LIGO detections. Our experiment is going to probe compact objects at much, much larger masses, but through a technique which is really analogous to the LIGO technique. So LIGO, as you know, searches for changes in the path lengths of these arms of this interferometer, right? So as a gravitational wave passes, the arms get longer and shorter. Our experiment is going to do a very similar measurement, sorry about that, but using pulsars as our detectors instead of lasers. And I'll talk more about the pulsar timing part of this in just one sec. But before I do this, let me just orient the NANOGrav experiment along with these other gravitational waves experiments. So this is your standard sort of gravitational wave spectrum. So on the y-axis is characteristic strain, and on the x-axis is frequency. And LIGO, of course, sits up here at tens to hundreds of hertz. Our NANOGrav experiment sits down at much, much lower frequencies. So we're sensitive to gravitational waves at about 10 to the minus 6 to 10 to the minus 9 or so hertz. I'll talk more about our source populations and our sensitivity curves later, but I just wanted to show that we're in a very complementary part of the gravitational wave spectrum to LIGO, and of course to LISA, which sort of bridges the gap between the LIGO and the NANOGrav experiments. Okay, so that is the big picture of what we're trying to do and kind of what we're all about. And I'd like to talk a little bit first about pulsars and pulsar timing. And then I'll talk about how we actually search for gravitational waves in our data. And then at the end, I'll present our most recent results. So pulsars are neutron stars. They're compact objects born in supernovae. And our experiment is a pulsar timing array experiment. That's just what it sounds like. So a PTA, or a pulsar timing array, is a network of pulsars distributed across the sky. And we observe these pulsars as an array looking for correlated signatures in the arrival times of the pulses from the different pulsars in the array. And you can use this PTA concept to do a lot of different types of experiments, but I'll be talking primarily about our gravitational wave search in this talk. I can't get away with a pulsar colloquium without playing our little pulsar movie. So the reason that pulsars are so good for this experiment is that they're phenomenally stable rotators. So here's the neutron star. We have a north and south magnetic pole, and radio emission is beamed along these north and south open magnetic field lines. And as the pulsar rotates, we detect a radio pulse for every rotation. Okay, so these make them like, cosmic clocks, and they're very, very useful for lots of different fundamental physics experiments, but in particular for detecting gravitational waves. So currently we know of almost 3,000 of these radio pulsars, and we can't time all of those to a precision that's sufficient for searching for gravitational waves. We can only use a subset of them called the millisecond pulsars. These are just what they sound like. These are the very fastest rotating pulsars with periods from about a millisecond to like 30 milliseconds or so. There's a little over 300 of these in our galaxy. We know there are many, many more in the galaxy. So if we could have, larger telescopes, more sensitive telescopes, we could grow our sample quite a bit. Out of the 340 millisecond pulsars that we know of right now, we're timing about 100 in total worldwide for pulsar timing array purposes. So not all of these are able to be timed with enough precision to be used for these fundamental physics experiments, so about 100 are. And I just want to show you two plots before I move on and talk a little more in detail about pulsar timing. This one here on the lower left, this is an ATOF plot of the galaxy. So this is the galactic plane here, and these are the north and south galactic poles. And the points on this ATOF plot are the positions of the millisecond pulsars. The red ones are the ones that we are timing for our pulsar timing experiment. And the reason I wanted to show this is just to illustrate that they're fairly isotropically distributed on the sky. And the reason for this is that they're a very old stellar population. So even though pulsars are born in the plane of our galaxy, these millisecond pulsars have had lots of time to move away from the plane. And they're also a fairly local population. All of the MSPs we use for our experiment are very nearby. They're mostly within like a couple kiloparsecs of the sun. So this is a very important property for gravitational wave detection, a very nice property. The other plot I just wanted to show is what we call the PP dot diagram on the right here. So this diagram shows all the pulsars that have been discovered thus far. This x-axis is spin period in seconds. So it's going from about a millisecond up to about 10 seconds or so. And this is period derivative. So this is the rate of change of that spin period. So as these pulsars age, their periods are getting longer and longer with time. And we are timing a subset of pulsars down here. So these red stars are the ones we're timing. And these are the millisecond pulsars. So they have very short periods and very small period derivatives. And they're extremely stable rotators. So it's an interesting story how they've ended up in this part of the diagram. We think pulsars are born kind of up here, with periods of maybe tens of milliseconds. And as they age, they move into this part of the diagram. And these pulsars down here have actually been recycled to very, very short periods through the accretion of matter and angular momentum from a companion star. So these are sort of like zombie pulsars or recycled pulsars. They're very, very old and very, very stable rotators. And most of them are in binaries with white dwarfs because of how they're formed. Okay, so let me talk a little bit about pulsar timing. And so when we time pulsars, we observe a neutron star with our radio telescope. Here's a little radio telescope. This is a very cartoonish diagram just to give you like a basic idea of what we're doing. We'll observe pulsars with a specific radio receiver on our telescope. We need to do a couple of things to the signal before we can actually measure a time of arrival. So this is what we want to get at. We want to know what is the time that this pulse arrived at our radio telescope on a particular epoch. The first thing we need to do is de-disperse the data. So this corrects for radio frequency dependent delays incurred as the pulse travels through the interstellar medium, through the free electrons that are in the interstellar medium. And the other thing we need to do to this signal is we need to fold it. So these pulsars are not bright enough to time them through their individual pulses. So we sum up all the pulses detected from a pulsar over something like a half an hour of observation to calculate a mean pulse profile that might look something like this. So a very high signal to noise profile. And then we cross correlate this with a high signal to noise template to measure this time of arrival. Of course, we have an atomic clock at the radio observatory that lets us measure this time of arrival to tens of nanosecond precision in the very best cases. So once we measure this TOA, we want to be able to model it. Okay, so we do what we call this calculating a pulsar timing model. And it's quite complex because of course there's lots of things that affect the arrival time of that pulse aside from simply the rotation of the pulsar, right? So the pulsar period is changing with time because it's losing energy. Most of our pulsars are in binaries with white dwarfs. And so this orbital motion gives that pulsar period a Doppler shift. The pulses are traveling through the interstellar medium. They're dispersed and everything is moving. The pulsar is moving, the Earth is moving, the interstellar medium is moving. So we need to correct for this in a time-dependent way. This dispersion measure is going to vary. And then of course, the Earth is going around the sun is moving. This gives us sensitivity to the position of the pulsar. We can measure a parallax for the most nearby pulsars to get a distance. And we have to fit for pulsar proper motions as well. We even have a contribution due to the solar electron density when our line of sight to the pulsar passes close to the sun. That will actually change this dispersion measure due to the free electrons in the solar ionosphere. So we have to put all of these things into a quite complex model. And so we take the times of arrival that we measure, we build up a timing model, and then we want to be able to predict the arrival time of every pulse at every epoch with very high precision. And so our timing models look something like this. I don't have time to go through every single row, but this is an example model for a particular pulsar. And just to point out a couple things, so we measure astrometric parameters like the right ascension and declination, the proper motion or the velocity of the pulsar in the sky, the parallax, which gives us its distance, spin down parameters, and just to illustrate how incredibly accurately we can measure the properties of these pulsars. For this particular pulsar, this spin frequency is 218.8118438547250 hertz. So we can measure the spin frequency of this pulsar all the way out to that very last significant digit. So this is really kind of like the state of the art for pulsar timing. We measure a spin down rate, and this pulsar is in a binary with a white dwarf. The orbital period is about 67 days. And so we measure Keplerian parameters. We also measure some relativistic corrections to the orbit, and I'll talk a little bit more about that in a few slides. The pulse profile shapes, so these shapes that we observe, which characterize the shape of our pulsar beam, actually change with radio frequency, so we need to correct for that effect. And once we have all of these effects in a model, we want to calculate what we call timing residuals, right? And so the residuals, just what they sound like, they're the differences between when a pulse arrives at a particular epoch and when our model predicted that it would arrive. So if we're doing a very good job and we're modeling everything exactly, we expect all of our residuals to be centered on 0. Okay, so this is an example plot. This is for the same pulsar as in the previous table. Note this scale, this is in microseconds. And this is over 20 years of data for this particular pulsar. And the different colors here are different telescope backend combinations. So this data is from the Arecibo Observatory. And most of this is from Arecibo actually, aside from these red and blue points, these are from Green Bank, the ones with G's here. And you can see that with time, over the 20 years of data for this particular pulsar, the error bars have gotten smaller. And that's because our radio bandwidths have got larger. The telescopes have stayed exactly the same size, but as we go to larger and larger bandwidths, we're able to measure the times of arrival more and more precisely. And you can see here the most recent data, and this is not a very up-to-date plot. It's just a nice 20-year data set that I could show. I'll show more up-to-date data in a little bit. You can see the error bars here for the Arecibo data. So this is a 300-meter telescope, or much, much smaller than these red error bars for a 100-meter Green Bank telescope. So the collecting area really makes a big difference. The main point of this plot, though, is just to show that we can time pulsars for decades. So this is 2 decades of data. The spin period of this pulsar is around 4.5 milliseconds. And we quantify how well we can time a pulsar from the root mean square of these residuals. And for this pulsar, that's about 70 nanoseconds. So that's pretty good. This is sort of the state of the art in pulsar timing right now. This is as well as we're doing really for any pulsar in our current array. Okay, so we talked about all these deterministic effects in our pulsar timing data. There are other effects in the data that we would characterize as sources of noise, however. And some of these are intrinsic. For instance, our pulsars aren't perfect rotators. They're going to have some timing noise. We also see an effect called pulse jitter. This is because every pulse does not show up at exactly the same pulse phase. They jump around a little bit. The emission mechanism is a little bit messy. The shapes change from pulse to pulse. That's another source of noise. These are both intrinsic to the pulsar. And there are other extrinsic sources of noise, like variations in dispersion measure, scattering, planetary ephemeroids. So we need very exact models for where all the planets in the solar system are at each epoch of our observation, so we can barycenter our data, so we can correct the arrival time to the barycenter of the solar system. And if that's wrong, that can be a source of noise. We could have clock offsets at an observatory. One of our clocks could suffer a little glitch, and we could have a few nanoseconds of time offset. In our modeling that we do, we can fit for all these different sources of noise because they all have different characteristics. So only one of these sources of noise we expect to vary with radio frequency. That's this interstellar medium stuff. Only one of them is not correlated in time. And only one of them, this planetary ephemeris source, is correlated in space. And by that, I mean we expect pulsars in the same direction of the sky to show correlated noise properties, if the planetary ephemeris was wrong. So we have a Bayesian analysis, which fits for all these different sources of noise in our data as well, in addition to this deterministic timing model. Okay, so I'm going to leave the pulsar timing for now and talk a little bit about gravitational waves, and then bring it all together and tell you about our data analysis and our most recent results. So this is a really nice little cartoon. This was created by Don Backer, actually, several decades ago. And he's really the founder of this pulsar timing array field and of NANOGrav. So here's our standard picture where we have a black hole binary. And we have two pulsars sitting in this warped space-time due to the gravitational waves being emitted by this black hole binary. Here's our telescope. And you can see just by looking at this like very simple little cartoon that the light travel time from pulsar 1 and pulsar 2 is going to be different than it would be in the absence of gravitational waves. And depending on the orientation of the pulsar, the gravitational wave source, and the telescope, this light travel time is going to vary, right? So this is a very similar concept to LIGO. The things that are different from LIGO are the strains that we're sensitive to and the frequencies that we're sensitive to. So the gravitational wave frequencies that we're sensitive to are going to be roughly like 1 over the cadence of our observations. So if we observe our pulsars like every few weeks, the highest frequency gravitational waves we can detect are going to be about 10 to the minus 6 or so, 1 over weeks. And the lowest frequencies are going to be 1 over the total time span of our experiment, which is like years to decades. So that gives us that low frequency nanohertz bound. The residual that we'll detect at our telescope, so the change in arrival time due to a gravitational wave, is going to be roughly proportional to the strain of that gravitational wave over the frequency of the wave. So there's this 1 over f term. And this is really important actually, because it means that as our experiment gets longer and longer and our time span gets longer and longer, we're sensitive to smaller and smaller frequencies, and the induced residuals are larger. So we kind of like automatically become more sensitive with more time as the experiment gets longer. We're quite different from LIGO in one way. When LIGO detects a gravitational wave, the entire LIGO arm gets stretched and squeezed. In the pulsar timing case, though, our gravitational wave wavelengths are much smaller than the distances between us and the pulsars. So we have many wavelengths in between the pulsar and the Earth. And so when we calculate the perturbation that we expect at Earth, we have to calculate a pulsar term and an Earth term. And the gravitational wave might have evolved significantly between that pulsar and that Earth term, which is kind of cool because we can see a gravitational wave source at 2 different points in its evolution. And just to get a feeling for the kind of strains we're sensitive to, we can turn this little equation around and we can say, well, if we time pulsars to precisions of say like a couple hundred nanoseconds, right, that's that delta t, and we do that over a decade, then the minimum detectable strains are going to be around 10 to the minus 15. So this gives you like a ballpark estimate of the strains that we're going to be sensitive to. And these are, of course, much larger than the strains that LIGO is sensitive to. But we can detect way more massive black holes. And here's this little, this is a cartoon sensitivity curve for NANOGrav. And it has a V shape, much like LIGO's sensitivity curve has a V shape. And so this most sensitive point here, this is going to be 1 over the time span of the data that we're analyzing. As we get to lower frequencies than that, we become less sensitive because we would just fit those perturbations out in our timing model. We won't be fully sensitive to them. This end up here, we're seeing this 1 over f term come into play here. And we have a peak here at 1 over a year. So this is a frequency of exactly 1 over a year. And we're not sensitive to those frequencies because we would fit year-long periods out when we fit for positions or proper motions in our data because they have a yearly signature in our pulsar timing residuals. Okay. So let's talk a little bit about gravitational wave sources. So we are going to be sensitive to very, very massive black holes. So we call these supermassive black holes with orbital periods of like years to decades. There's a lot of evidence that these kind of systems exist. This is a Chandra X-ray Observatory image of an X-shaped galaxy with these sort of X-shaped jets, which we think are due to two black holes at the core. And we know that every galaxy has a black hole. We know that galaxies must merge. So there should be a substantial population of these objects out there for experiments like ours to detect. If we look at this strain that we expect due to a binary system, we expect a strain of around 10 to the minus 17 if we have black holes of mass 10 to the 8 solar masses with a frequency of 1 over a year at around a gigalight year distance. This is just this Q is the mass ratio between the two. This looks pretty small, right? This is a lot smaller than the 10 to the minus 15 that we just saw on the previous slide. This means that we need very, very massive systems in order to detect a single gravitational wave source. If we do detect a single source, we'd be in the continuous wave regime. So it would look something like this. Over the time span of our experiment, over just decades, we wouldn't really expect a lot of evolution. So we'd see like a non-evolving sine wave in our timing residual, something like this. We can also detect burst sources, so single merger events, and that would look like a step function in our residual. And again, this would have to be a very bright event to see with our current sensitivity. But let me just point out one thing. So I also have the time to merger here. So while the strain of these sources is smaller, if we have smaller frequencies, those systems are going to take a lot longer to merge. So if we look at a different type of signature, a stochastic background, so this is the superposition of the signatures of all of the supermassive black hole binaries in the universe that are merging. We expect that to have a characteristic strain spectrum, which looks like a power law. And we expect that spectrum to be red. So what that means is that even though for an individual source, a high frequency individual source will have a higher strain, those objects are going to merge much more rapidly. So when we look at this background of gravitational waves, we expect it to have a red spectrum or have a negative spectral index. So it'll be dominated by all the very long orbital period supermassive black hole binaries. And this stochastic background is what we think we'll detect first in our NANOGrav data. This superposition of all of the signatures, all of the gravitational wave signals from all of these supermassive black hole binary mergers in the universe. And in this little cartoon, we expect it to look like noise. It'll look like red noise, but we can distinguish it from other sources of noise because it will be correlated among the pulsars in the array, unlike these other sources of noise like intrinsic pulsar timing noise or stuff due to the interstellar medium. So let's talk a little bit about what that signature will look like. So this is a very famous curve called the Hellings and Downs curve. This was published all the way back in 1983. And what this shows is the correlation between residuals from a pair of pulsars versus angular separation. So if we have two pulsars that are separated by 0 degrees, they're in exactly the same direction of the sky, we expect their residuals to be correlated. If they're separated by roughly 90 degrees, and because of this quadrupolar nature of gravitational waves, we expect anti-correlated residuals. And back at 180 degrees, we expect a correlation again. And the exact shape of this was calculated by Hellings and Downs. And you basically need to integrate over an isotropic distribution of supermassive black hole binaries to get this exact shape. But this quadrupolar signature is quite easy to understand just looking at this simple little cartoon. And the really nice thing about this Hellings and Downs signature is that it's very hard to get this if you don't have an actual gravitational wave source. So we could have, clock errors in our data, for instance. A clock in an observatory could be off, but that would be a monopolar correlation. We wouldn't expect any kind of sky correlation with an error like that. The only error that we can think of aside from gravitational waves, or the only source of noise, would be an ephemeris error. So say we have the mass of Jupiter wrong in our ephemeris model. Well, we would expect pulsars at 0 degree separation in the same part of the sky to show correlated residuals, but we'd see anti-correlated residuals at 180 degrees, not 90 degrees, right? We'd see an anti-correlation for pulsars in opposite directions of the sky. And gravitational waves are really the only thing that we can think of that would produce this exact quadrupolar correlation. So this is the signature that we're looking for in our data, this quadrupolar correlation due to these gravitational waves passing through an isotropic distribution Actually, let me step back. I didn't mean passing gravitational waves from an isotropic distribution of supermassive black hole binaries. And we'll talk more about the pulsar distribution in a minute that we need to detect this. Okay, so let me just show this table again. So this is the same table that I showed before. And the previous table had the intrinsic and extrinsic sources of noise. And now I've added the gravitational wave background on here. And so you can see that this gravitational wave background, which will look like noise in our data, has some of the same properties as other noise sources. It's going to be achromatic. It's not going to depend on radio frequency. It will be correlated in time. It'll be correlated in space, just like ephemeris errors, but it's the only one that's going to show this specific quadrupolar correlation. So our analysis fits for all of these different types of noise in our data in order to tease out the exact signature of a gravitational wave background. And I'm just going to show a little movie before I move on to talking about our NANOGrav results. So in this movie, we have two galaxies that are merging. And at the core of each of these galaxies will be a black hole. And you can see the gravitational waves that are being emitted by these black holes as they come together. And if any of you are an animator or know a really good animator, we really need a better, higher quality video. This is the best thing we have right now. And as these gravitational waves at the cores of these galaxies begin to merge, these gravitational waves are going to travel through the universe. And just to make this clear, the supermassive black hole binaries that we're seeking to detect with NANOGrav are very far away, right? So they're cosmological, maybe gigaparsecs away. All the pulsars that we're timing are within our own galaxy, so very nearby. And as the gravitational waves pass between the Earth and the pulsar, they're going to redshift and blue shift the apparent spin period of the pulsar. And so this is a nice little illustration of the kind of effect that we're looking for. And I wish we had a radio telescope that big. That would be really nice. We would have already detected gravitational waves many years ago. Okay, so hopefully I've laid out what radio pulsars are, how we do our pulsar timing experiment, and how gravitational waves will look in our data. And now I'd like to talk specifically about our NANOGrav data and our most recent results. So our experiment has been taking data for something like 16 years now. And very recently, as I'm sure you've heard, we lost the Arecibo Observatory in Puerto Rico. Up until August 2020, when one of these cables broke, we were observing about 80 millisecond pulsars. And we were observing them at two frequencies. And we need to observe at two separate radio frequencies to correct for these dispersive effects due to the interstellar medium. We were observing about every 1 to 4 weeks, depending on the pulsar. We'd look at each pulsar for about 20 to 30 minutes. We did about half of the pulsars using the Arecibo telescope in Puerto Rico over here, and about half using the Green Bank telescope in West Virginia. This is the one that's in my backyard here at West Virginia University. And we did a couple pulsars at the very large array, well, more than a couple, 7, at the very large array in New Mexico. And this is a little cartoon which shows the distribution of the pulsars on the sky. This blue band is the part of the sky that's visible with Arecibo, and the green, the GBT, and we can't see anything in the southern hemisphere down here, so we rely on our IPTA partners to cover that part of the sky. This line here is the galactic plane, and you can see lots of our pulsars are sort of centered near the galactic plane. And the distribution could be more isotropic. We're trying to carry out searches in these holes where we don't have many pulsars and we don't have a lot of sensitivity. So our observing program changed pretty dramatically back in August 2020. We haven't been able to use Arecibo since that time. In December 2020, it completely collapsed. And this is a picture of the dish after the platform crashed through it. And this was just obviously really catastrophic for us. We had a baseline of 16 years of very sensitive data taken with this telescope. And so we've been left at a bit of a loss. Up until about a month ago, we were just carrying out our Green Bank telescope program. So we just couldn't observe the Arecibo pulsars anymore. Very recently, we've got a little bit more time on this Green Bank telescope to add some of the Arecibo pulsars to the Green Bank program. And we've dropped some of our low frequency Green Bank observations because we have a new telescope in China, in Canada called CHIME. And this CHIME telescope covers the low frequency band that we were covering with the GBT. This is a lot of details. If you're not radio astronomers, this may not be super interesting, but we've been really trying very hard to take the amount of time that we have on the Green Bank telescope and try to maximize it so we can get as many of these Arecibo pulsars added back in to the timing program. We're also talking to collaborators in China. There's a very large telescope in China called the FAST telescope, about trying to get some of our pulsars observed there. Some of the very faint ones that we can't observe with the Green Bank telescope because it's just too small. And so this is the general plan. We observe about 80 millisecond pulsars every couple weeks. And we release data every couple years. So the way we work is every few years, we'll put out a new data release to the public. And this plot over here shows our previous data releases. So our first one was 5 years of data. We had 17 pulsars in that initial data release. Our second 9-year data release had 37 pulsars. Our 11-year release had 45. Our most recent one, our 12.5-year data set had 48. And we're currently working on a 15-year data release with something like 65 pulsars. The different colors here are just different radio frequency telescope combinations, and these are all the different pulsar names. I don't expect anyone to read all of these names right now, but the main thing that I want to point out is just that we keep finding new pulsars and adding new pulsars to the data sets. So each data set has more pulsars than the previous. We've also increased the cadence of our observations a lot. So you can look back at the old data and you can sort of see that these points are spaced by a month and there's a couple big gaps. The more recent data, we're observing many pulsars at less than a month cadence. So these look more like just kind of solid lines. And this has really dramatically increased our gravitational wave sensitivity. If you're interested in these data, you can go to data.nanograv.org. It's all public. Our most recent 12.5-year data set is completely public. You can download it. I can help you find the right codes to read it in and analyze it if you're curious about doing that. We really want people to use these data releases. And I just want to take a minute to point out that aside from times of arrival, which looks something like this, so these are the kind of data that you will download if you want to get TOAs, you get a whole bunch of modified Julian dates out to very high precision, like these. They're just text files. There's a lot of other data, though, that people might be interested in. We have very, very high sensitivity polarimetric profiles for pulsars. Here's an example of a millisecond pulsar at lower and higher radio frequency. And we have these very high sensitivity, very complex profiles available. These are polarization position angles. We detect some very, small scale structures in the polarization that have never been seen before that can be really useful for probing pulsar emission mechanisms. And so those are all available. We also have parameter files available. So for each pulsar that we time, we have a list like this, which gives the pulsar position, frequency derivative, binary parameters. This particular pulsar, 0740 plus 6620, has been in the news a lot over the past year because we measure a Shapiro delay signature. So these are the timing residuals from this pulsar. This is the signature, this delay here is the signature of the pulsar passing behind its companion white dwarf star. And so as the pulses from that pulsar travel through the gravitational well of the companion, we see a delay. And from that delay, we can measure the mass of the pulsar and its companion. This particular pulsar has been really interesting because the mass constraint we get is quite high. It's more than 2 solar masses. It still has quite a large error bar. This blue band is the error bar, but it's higher than any previous measurements for any other pulsars. So this shows neutron star mass versus radius, and these lines here are different equations of state. So this has been very exciting to the broader community because we're able to rule out some equations of state from this measurement. With time, these error bars will get smaller and smaller, and this will get more and more interesting. And we hope to make similar measurements for many of the other pulsars in our array. Okay, and there's tons of other things that one can do with our data. You can probe the interstellar medium, the solar wind. You can do astrometry with all the parallaxes and proper motions that we've measured, for instance. Okay, so let me talk about our most recent results. So these are examples of some of the residuals that we measure. And so again, these residuals are the data that we search for gravitational waves in. And these are the differences between our model times of arrival and our measured times of arrival, right? So again, if our model is absolutely perfect and there's no other features in our data, we expect all of these residuals to sit nicely at 0. And again, the y-axis scale on these is in microseconds. And these are just 3 kind of random pulsars from our most recent data set. These dotted lines are when we switch to better instrumentation. So you'll see improved error bars after these dotted lines. And what we do in our experiment is we take the residual of every pulsar and we cross-correlate it with the residual of every other pulsar to see if we detect this quadrupolar correlation in our data. And you can see clearly that there is stuff in this residual for all 3 of these pulsars, that we don't understand. There are some points that are not consistent with 0, and that's okay. They'll be modeled out as other sources of noise. What we're searching for in the gravitational wave signature is correlated noise among all of these pulsars. And so I'm going to talk mostly about our stochastic background results, which will look like correlated red noise in these residuals. We also search for sine waves from single sources or step functions, which we expect due to gravitational wave bursts. And all of these would be correlated among all the pulsars in the array. So our most recent results are from the 12.5-year data set, but I'm just going to talk about our last data set first, our 11-year data set, because it's a really interesting story. So when we carry out this analysis, the end product is a PDF, a probability density function versus gravitational wave amplitude. And when we first carried out this analysis for our last data set, our 11-year data set, we used a fixed solar system ephemeris. So we get solar system ephemeris from the Jet Propulsion Laboratory. These colors here are for different ephemeris. And if you look at these curves here, this is what we calculated originally for our 11-year data set. So we just use one ephemeris. We use this DE436, and you can see this red dotted line here. So this is the PDF versus gravitational wave amplitude. This looks really exciting, right? This looks like a detection. This peaked at a particular gravitational wave amplitude and fell off on either side. This was really exciting. We thought we may have detected gravitational waves. And of course, the first thing we did was say, let's see if we can make it go away, right? What can we change in our analysis? And so we tried different models, right? So different ephemerides. And we found that we had very different amplitudes and very different PDFs for different models, right? So that's bad. So none of these were consistent. And this caused us to realize that the ephemeris we were getting from JPL aren't accurate enough for our purposes. And so we had to develop a new code. It's called Bayes-Ephem, because it models these ephemeris errors in a Bayesian way. And these are the results from our new Bayes-Ephem code. And so basically this code fits for the dipolar correlation due to an incorrect ephemeris at the same time as it fits for this quadrupolar gravitational wave correlation. And when we applied this new Bayes-Ephem code, our PDFs looked more like this. This no longer looks like a detection. You can look at this right plot, which shows Bayes factor instead of PDF. And the Bayes factors for all of these PDFs are just about 1, which shows that this is just consistent with noise. This is an upper limit, not a detection. All 4 of these lines are consistent. So regardless of which starting ephemeris we use, we get the same final answer, which is very, very reassuring. And so this was the result of the 11-year analysis. Even though we didn't detect gravitational waves with that data set, it was still pretty interesting because we could do astrophysics with it. So our limit was sensitive enough that we could actually rule out some models for how supermassive black holes come together, how galaxies merge. And so this plot here shows strain versus frequency. These bands are 3 different astrophysical models that have different assumptions about the roles of stellar scattering, the roles of gas in a disk in bringing these black holes together, and the eccentricities of the binaries. And we can rule out one of these models, this model with the green band here, already from our 11-year data set. Because if this model was correct, we should have already made a gravitational wave detection. So that was very exciting. We can constrain things like relationships between black hole mass and bulge mass. There's several different published predicted relationships between the two. And we can say the ones that have high predicted black hole masses are very unlikely, or we would have already made a detection in this 11-year data set. Okay, so that was the 11-year data set. We went into the 12.5-year data set, not quite sure what we would see. We thought that we would probably have another upper limit and we'd be able to set even more robust constraints on the astrophysical processes bringing these black holes together. And that is not what we found. So we have a very different result with the 12.5-year. This is an analogous plot. This one over here shows the PDF versus gravitational wave amplitude. And unlike this data set where we very clearly have an upper limit, right, with these solid lines, these look like detections. So there are two different types of curves here. So these two solid curves here are for a fixed solar system ephemeris, so not using our BESA-FEM code. This is the most recent JPL ephemeris, and this is one from the IMPOP group in France, and they're very consistent with each other. The dotted lines are using our BESA-FEM code, which fits for errors in these ephemerises. And you can see that both of these, both of them peak at a particular amplitude, right? So neither of these look like upper limits. And what this means is that we're detecting a very strong common red noise process among all the pulsars. So there is some source of noise that is common to all of the pulsars. That's very exciting. However, we cannot yet say that this is gravitational waves. And the reason for that is we can't yet distinguish the quadrupolar signature. So on the left here are the fits of our data. So these black points here are our residuals, our correlated residuals. These are averaged in 10 degrees bins. This isn't how we actually do the analysis. We would have many, many, many points on here if we showed you all the data, but this is just sort of to guide the eye. And this blue dotted line is the best fit Hellings and Downs curve. This is for the 11-year data set. And the one at the bottom here is for the 12.5-year data set. Neither of these, look exactly like this Hellings and Downs curve. You can see that the error bars have gotten smaller from the 11-year to the 12.5-year. So that's very promising. In particular out here at this very high angular separation regime. And, maybe if you really want to be optimistic, you can say, it looks like they're hugging this line a little bit more, but there's really, we do not see a quadruple correlation either by eye or through a statistical analysis. We see a very strong source of common red noise though, which is what we would expect if it's the first sign of a gravitational wave background. That is what we would see first before we see the quadrupolar correlation. If what we are seeing is indeed a gravitational wave background, we can simulate when we would actually detect it with high significance in our NANOGrav data set. And so if the amplitude is what we measure currently, which is about 2 × 10⁻15, that's this horizontal line here, in our 15-year data set, which sits here, we should detect the correlated signature at a signal to noise of like 4 to 7, something like that. So in our next 15-year data set, we should see this quadrupolar correlation if this is indeed the gravitational wave background. So this is very exciting. Of course, with time, our measurement will improve. And the measurement of the amplitude of this signature and also of the spectrum of this signature will give us unique constraints on galaxy formation and evolution. And so then we'll really be able to do astrophysics again. And one somewhat disappointing thing about the 12.5-year results is unlike our 11-year data set where we could draw astrophysical inferences, we can't do that with the 12.5-year data set because we don't know what this source of noise is. So we can't use this to improve our knowledge of galaxy merging and evolution until we figure out what the source of this noise is. And we hope to have done that in our 15-year data set and actually glean astrophysical insights from it. I don't want to go too much on. Let me just talk a little bit about our continuous wave search before I end. So, we're looking for other sources of gravitational waves in our data. In addition to the stochastic background, we look for single sources, and our single source results look something like this. So this is an ATOF plot of the galaxy. These stars are our pulsars. And so you can see we have a lot of pulsars in this part of the sky, not very many in this part of the sky. And this color is our sensitivity. So what this means is in this part, we're like very sensitive because our most sensitive pulsars are right around here. We can make constraints out to about 120 megaparsecs. We can say there are no billion mass supermassive billion solar mass supermassive black hole binaries out to about 120 megaparsecs in this part of the sky at the frequencies to which we're sensitive. In this part of the sky where we're less sensitive, we can go out to about 20 megaparsecs. But still, we can make statements. For instance, if the EHT detected black hole in the Virgo cluster was a binary, we would have detected that. We can say there are no supermassive black hole binaries with masses greater than about 1 billion solar masses in that direction of the sky. So this is getting exciting. We're able to make constraints that are actually astrophysical. This shows our sky average sensitivity versus frequency. You can see we're getting more sensitive from our 5 to our 9 to our 11-year data set. And we recently hit a very exciting milestone where for the first time, we took properties of a supermassive black hole binary that were measured electromagnetically by this group with very large array data. This is to a radio galaxy called 3C66b. And these authors, Iguchi et al., have suggested that there's a supermassive black hole binary at the core of this galaxy. And given their, there we go. So they have predicted a mass and orbital period for this black hole binary. We can take their electromagnetically inferred properties, put them into our gravitational wave pipeline, and use them as priors in order to do a gravitational wave search on the data. And this shows the results of that. So these blue, this blue line here, this is our posterior, taking their measurements as priors and searching our data for a gravitational wave signature. This horizontal line here is the upper limit on the mass of this binary. So it's about 1.6 times 10 to the 9 solar masses. This is their mass estimate, which unfortunately lies below our upper limit. So we cannot yet say whether this binary exists or not. This orange band here is the allowed range for their masses, but we're quite close actually. And so this is very exciting. And within a few years, we'll actually be able to place a constraint on whether this electromagnetically identified binary is real or not. So that's very exciting. And there'll be more of these, of course, that'll be identified electromagnetically over the next 5 to 10 years. Okay, I'm going to skip over this because I'm running out of time. And I just want to end with a few final slides. So I want to talk a little bit about like the next decade and how we're going to increase the sensitivity of our experiment. So if we want to make a detection faster, if we want to characterize the gravitational wave universe faster, what do we want to do? And it's really fairly simple. So the sensitivity of our experiment depends on only a couple very simple parameters. It depends on the number of millisecond pulsars in the array. So the more millisecond pulsars we're timing, the more sensitive we are. It depends on the time span of the experiment. So the longer our experiment goes, the more our sensitivity increases. It increases for higher cadences, and of course, with higher precision timing. Don't worry too much about my automatic light. I have a motion sensor and I think it's gone off, so it suddenly got very dark here. And I'm just gonna like wave my arms. Oh, come on. I think it's gonna come back. Okay, I'm gonna sit here in the dark. Oh, there it goes. Okay, so don't worry too much about these coefficients. These have very specific assumptions about the ratio of the background strength to our sensitivity. But the things on the top will always be on the top, and the things on the bottom on this equation will always be on the bottom. We'll always do better with more MSPs, longer time spans, higher cadence, and lower RMS timing residuals. So our plans for the next decade, we'd really like to grow the size of our array. Right now we're at about 80 millisecond pulsars. We'd like to get up to about 200 within the next decade. So we have a big focus on carrying out pulsar surveys. This has been affected a bit, of course, by the collapse of Arecibo, but we're working with international collaborators on pulsar searches with lots of other telescopes. And this will really like even out our sensitivity curve. So the number of pulsars versus angle to fill in that sort of high angle part of that Hellings and Downs diagram where we have those very large error bars. So this is going to be really important for characterization of the background. Another thing that we're working on very hard is to develop a wideband receiver for the Green Bank telescope. So right now we need to observe in 2 separate radio frequency bands. We observe down here and we separately observe up here. And our radio receiver actually cuts off right around here and we don't even get this part of the band. We've received funding from the Moore Foundation to develop a new receiver for the Green Bank telescope. The GBT engineers have been working very, very hard on this, and this is almost ready to go. It'll be commissioned next year. This is going to make our observations way more efficient because we can just observe once for each pulsar. We don't need like two separate observations at two separate radio frequencies, and we'll be able to correct for the dispersive and effects of the interstellar medium much, much better. We're also working really hard to incorporate CHIME data from the CHIME telescope in Canada. This is underway right now. It's not going to be in our 15-year data set, but it'll be incorporated in the data set after that. And this should really dramatically increase our sensitivity. This telescope observes all of our pulsars every day, right? So we're going to have a lot more data from this Canadian telescope to add to our data set. And of course, we're looking for a replacement for Arecibo. And we think this will take the form of what we would call like a large N small d array. So an array of many small telescopes. One concept that would work really well for us is this DSA 2000 telescope. So this is the Deep Synoptic Array. There's 2,000 small dishes. So we're working really hard to get something like this, built in North America, because once we've detected gravitational waves, the next step is characterizing the gravitational wave sky. And for that, we need to observe many pulsars as often as possible. And so we really need a telescope like this. And finally, I just want to come back again to this IPTA concept. We're not the only ones in the world doing this experiment. And another huge focus of ours going forward, especially now that we don't have Arecibo, is to work with international collaborators using large telescopes in South Africa, India, China, Australia, and Europe to combine all of our data into one uber sensitive data set that'll really be the most sensitive in the world for low frequency gravitational wave detection. And so within 2 to 3 years, we hope that this IPTA data set is much more sensitive than the NANOGrav data set alone. And sorry, I think I went a little bit over. I'm just going to leave this summary slide up. And I'd like to thank you again for inviting me to talk, and I'm very happy to take any questions.
Well, thank you very much indeed, Maura, for a very exciting and accessible presentation. I'm sure there'll be lots of questions, and I'm going to ask people to put up their hands. Maybe I could just start with the first one. It doesn't matter a question, just an opportunity to say just a little bit about the other use of pulsar timing for physics is for testing general relativity, the strong principle of equivalence, the gravitational radiation from Hulse-Taylor and other binary pulsars. What do you see as, could you just summarize very briefly for the audience what's been done and what you see as the prognosis for that going forwards?
Yeah, so some of the pulsars, which are the very best for testing general relativity, are not the same ones that are in our NANOGrav experiment. So I'm also part of a project where we are timing the double pulsar system. This is a system of 2 pulsars in orbit around each other. It's not in our NANOGrav array because the pulsars are, the periods are a little too long to be true millisecond pulsars. But that pulsar system is in a 2.5-hour orbit. And we can measure the rate of decay due to the emission of gravitational waves to incredible precision. It's the best strong field test of general relativity that exists. If you're talking just purely based on precision, it's better than the LIGO measurements. It's sort of 1 part in 10 to the 5 test of gravitational wave emission. So that's very exciting. Another system, which I would just highlight, is a triple system. So we're timing a system of a pulsar that has 2 companions, and we can actually test the strong equivalence principle with this system better than with any other system. This is also not part of our NANOGrav array because the triple system makes it very complicated to model the timing. That's sort of a source of noise. But we have one companion star that's very close to the pulsar and one that's very far away. So we can test the strong equivalence principle with that system. We measure Shapiro delay for a number of pulsars, where we see the light bending around the white dwarf companion. That's a very exciting relativistic measurement that we can make for many of the pulsars in this array. And I'd be happy to talk, it's kind of like a whole other colloquium to talk about the double pulsar or these other tests. But yeah, pulsars are really remarkable with all the fundamental physics we can do.
So thanks. I'm really glad you got explained that. That's great. Jeff Scargill, you have your hand up, I think.
Yes, thanks. Yeah, very nice stuff. I have two questions about what I guess you call the timing noise for individual pulsars. If I remember right, part of it is discrete so-called glitches that are very sudden changes, and presumably those are pretty easy to take out because it affects only one of the many pulsars at a time. Does your modeling explicitly remove glitches in that sense?
It would if any of our pulsars exhibited them. So none of the millisecond pulsars that we're timing have shown detectable glitches so far. Most pulsars that show these glitches are younger pulsars. So we don't have to include glitches for any of the pulsars in our experiment so far. What we see is more like red noise, just due to kind of long time scale instabilities in the pulsar rotations.
Right. And so I kind of missed how you distinguished common red noise just being a common feature of the way pulsars are spinning, as opposed to a gravitational radiation signal. What?
Yeah, so we calculate power spectra for all of the pulsars in our array, and we characterize those spectra with an amplitude and a spectral index. And we fit for two contributions. We fit for one that's independent to each pulsar, and then one common spectral process with the same amplitude and spectral index in all the pulsars. And so for each pulsar, we have this common spectral signature, and then a signature that's individual, to each pulsar. So we basically calculate a common spectral process in addition to a process for each individual object. Does that make sense?
It sort of does, but I mean, so if all pulsars, for example, had the same red noise with the same slope in the log power versus log frequency, how would that be distinguished? How would that common spectrum noise be distinguishable from what you're calling common?
It wouldn't have this quadrupolar signature.
Oh, okay.
So we're looking specifically, there's a couple different, so we're looking for a common process that has this quadrupolar signature. So in the 12.5-year data set, our current data set, we can't distinguish that quadrupolar signature. We can tell there's a common process. All of the pulsars show a common source of noise with the same spectral index, right? But we can't distinguish the quadrupolar correlation yet, right? So it still could be, right now it's consistent with them all having intrinsic timing noise, but with the exact same spectral index, which would be unusual, but not impossible. In our next data set, we should be able to tell whether that common spectral process shows this quadrupolar signature.
Got it. Thank you.
Roger Romani, you have your hand up.
Yeah, sure. Hi, Maura. Good to see you.
Hey, Roger.
I had a question about whether VLBI could be helping with this very much. For example, your new pulsars, sometimes you have better positions and parallaxes out of VLBI than you got from the timing. But I'm wondering, VLBI has come so far along, is it possible that you could actually improve the sensitivity and the parallax and position peaks by using VLBI positions instead of fitting them out in the data?
Yeah, that's a really great question. For some of our pulsars, indeed, we can do better with VLBI than through timing. That's actually a project one of my students is working on. So instead of using the timing derived parameters, using VLBA priors that have much smaller error bars, that will improve the overall timing. The way VLBI might really help us though is with the single source detection. So if we want to be able to localize single sources, so a single supermassive black hole binary, we need to use not just the Earth term, but the pulsar term in our residuals. And in order to use those pulsar terms, we need to know the distances to the pulsars in our array to within a gravitational wave wavelength.
Yeah, that's pretty
which
tough.
is like, yeah, which is like
that's a 1/10%. That's going to be
yeah,
a while.
Right. So we're talking like parsecs.
Yeah.
We know the distance to one pulsar that well, or 437. In time, though, we're talking like decades. VLBI may be able to give us the exact distances to enough pulsars that we can then use them to localize gravitational wave sources. Right now, if we detect a single gravitational wave source, if we don't have an electromagnetic prior, we're going to have a huge error bar on the position, like much bigger than LIGO. But if we can measure the distances to those pulsars, either through timing or interferometry, then we'll be able to localize gravitational wave sources way better. So I think that's where VLBI is really going to be important for us.
Georgia
Thanks.
Grata, you have your hand up.
Yes, thanks, Roger. So first of all, I apologize. I don't have a camera with this setup. Well, thanks very much for the very nice talk. Even for a non-expert like myself, it was really very instructive. I'm intrigued by byproduct of what you're doing. That is the ephemeris. It seems to me like maybe I'm not getting this right, but the different models from JPL are much closer together than your fit. So that means that presumably you found, if I get this right, that they are wrong essentially. Is there any application in having to do with solar system dynamics or something?
Yeah, that's a really good question. When we first realized this, we were very excited and we thought, wow, these JPL people are going to really, they're going to want to use our measurements, and we talked to them. But there's a couple issues. The first one is that their models are sufficient sensitivity for what they want to do. So if they want to land a spacecraft on a planet, their models they're okay. They only care about localization to within 100 meters or so. We need better than that for our data sets. So their models are sufficient for their purposes. The second problem, which is really bigger, is that what we're measuring through our experiment is different from what they're measuring. So what we're measuring is the location of the center of the solar system, of the solar system barycenter. So we can localize the barycenter of the solar system to within like 100 meters, but they don't care about the location of the solar system barycenter. They care about the location of Jupiter at a particular time. So our reference frames are a little bit different. So it's not like we are measuring an ephemeris in the same way that they measure an ephemeris, if that makes sense. Like we're measuring the barycentric position, which is different than what JPL measures. And just as an aside, right now Jupiter is the main source of error in our experiment, and this is all going to go away because the Juno satellite is measuring the mass and position of Jupiter very, very accurately. So we expect future ephemerides produced by JPL to be consistent with what our base FM code gives us going forward. So this problem should kind of go away. Actually, they won't need us anymore anyway, because they're measuring it very precisely. If that makes sense.
Okay, thank you.
Well, thank you, and I'm not sure whether that happens or not, but it's certainly a very impressive future in front of us. So thank you very much, Maura. Let's give you a virtual round of applause and welcome you to visit in person as soon as that becomes practical. So good luck with the future, with the 15-year data set.
Thank you very much, Roger. Thanks for inviting me. And feel free to email me, if anyone has any questions or wants to follow up. Happy to chat.
Thank you. Take care.
You too. Thank you.